In this lesson, we're going to talk about dissociation and ionization. Now, quickly here, dissociation, that is a term specifically for ionic compounds. And it talks about ionic compounds when you throw them in water. If they are soluble in water, if they dissociate, they break apart into their ions. With ionization, it's a similar process except for it's for molecular compounds specifically. So if a compound ionizes, what that tells you is it's a molecular compound that's going to break apart into its ions. Okay, so that's the main difference between the two terms here. Dissociation is when ionic compounds break apart into their ions. Ionization is when molecular compounds break apart into their ions. So since these are both terms that you're going to want to know, let's make sure that we highlight it. So as we've said, dissociation is the separation of ions that occurs when, that should be ionic compounds, dissolve in water. Okay, so keep in mind, dissociation is a part of the dissolving process, but they are not necessarily the same. They don't mean the same thing. Okay, so a dissociation equation is used to show an ionic compound breaking apart into ions in water. Just like other chemical equations, it needs to be balanced. So let's make sure to highlight that. All right, so for ionic compounds and bases, first off, we need to figure out, okay, what is a strong base? And a strong base, all it is a metal bonded with hydroxide. So it could be any metal, could be sodium hydroxide, potassium hydroxide, so on and so forth. Okay, and we need to figure out, okay, what are going to be our high solubility ionic compounds and bases compared to our low solubility. So for high solubility ionic compounds and bases, they're going to dissociate into two ions. It's always two. It's never more than two, just two. And the two ions that are going to be produced when dissociation occurs is going to be the cation and the anion. So the positive ion and the negative ion. So there's a nice little dissociation equation right here. Okay, so let's write a note. It's only ever two. So high solubility compounds dissociate readily in solution, and we show the ions only. Okay, so with this, what we're going to do in order to figure out, okay, is an ionic compound soluble in water or insoluble in water, we're going to go to our Chem 30 data booklet. That's the one with the orange cover that looks like that. Okay, and we're going to go to page 6, and this table at the top is going to be what we're looking for. Okay, so there is a solubility table on the second page of the Nelson periodic table sheet. However, I'm going to recommend that you use the Chem 30 data booklet. First off, just to get you more familiar with this data booklet if you are looking to go into Chem 30. And second, the reason why I'm going to recommend that you use this table is there are some minor differences in between the solubility table on the Chem 30 data booklet compared to the Nelson periodic table. And just for consistency, I'm going to say stick with the Chem 30 data booklet solubility table. Okay, so for some of the examples that it gave, so looking back here, we have, even though, oh, there we go. We have sodium chloride solution, okay? So to determine if sodium chloride, even though they are showing us, yeah, it does dissociate, how you would figure that out if you didn't have that already done for you is, in order to determine if an ionic compound is going to dissociate, you need to first determine if it's soluble in water, okay? If an ionic compound is soluble in water, it will dissociate. So, as I said in a previous lesson here, we're going to want to start by first finding our anion and then our cation. So our anion, that's a negative ion. For sodium chloride, the anion is going to be chloride. So then we trace our finger down, and okay, most things with chloride are going to be very soluble. However, before we go off and be like, yep, sodium chloride soluble, right, you just want to double check the lists of exceptions to make sure that sodium or your cation in general isn't part of the exceptions. Because if you find your cation in the bottom row, it's going to be insoluble, okay? But since sodium isn't in the bottom row, it's going to fall under most, so then that's how you know for sure it's going to be soluble, okay? And if an ionic compound is soluble in water, we represent just the ions that it breaks apart into. Okay, so that's why they have it as sodium 1 plus aqueous, and then the chloride ion aqueous. So aqueous, what that means, just as a quick reminder, AQ, didn't write that very neat. AQ means aqueous. And all that means is that it's dissolved in water. Okay, if we were figuring out magnesium nitrate, how you would know it is soluble in water besides the diagram there is first we would find nitrate, our anion, and then trace our finger down. Okay, most things are soluble with nitrate. However, we just want to double check the exceptions. Magnesium nitrate's not in our list of exceptions. Therefore, that's why we would write the state as aqueous, and also since it's an ionic compound that's soluble in water, that means it's going to dissociate, so that's why we represent the ions. Okay, so sodium hydroxide, that is soluble in water. Where we're finding that is we look for hydroxide, which is right here, and it says group 1 ions. Okay, so group 1 ions just means, if we go to our periodic table, so these numbers across the top here, they're just talking about the group numbers. So group 1 is right here. So anything in this first column here, let's highlight it. Anything in this first column here is in group 1. So what it's saying is anything, like it could be lithium, sodium, potassium, rubidium, cesium, or francium. If any of those are with hydroxide, it's going to be soluble in water. Okay. So let's go back here. Okay, as well as this is also saying any group 1 ion, or if it's ammonium, it's going to be soluble in water. Okay, so since sodium is in group 1, that's how we know it's very soluble. Now, one of the differences between the Nelson periodic table solubility table, which is right here. Okay, so it's on the second page in the top right-hand corner. So the difference between this solubility table and this solubility table is if we look for barium hydroxide on the Chem 30 data booklet. So hydroxide is right here. Barium is actually a group 2 ion. So barium is right here. So it doesn't fall under our group 1 ions, nor is it ammonia. So for this solubility table, barium would actually fall here under most, and it would be insoluble in water. Okay, so with this, that's where some of the differences are being made, because if we did the exact same thing with the Nelson solubility table, hydroxide, you see barium listed right there as something that's going to be very soluble. So just keep that in mind, since I am recommending that you use the Chem 30 data booklet over the Nelson periodic table booklet, or data sheet I should say. We are going to say that this is actually insoluble, but just keep in mind there is a slight difference between the two solubility tables. So we're going to say use Chem 30 data book for a solubility table, just so that we have some consistencies. So it's on page 6. So this should be barium hydroxide, and since it's insoluble in water, we would just write it as S for solid. Okay, so some low solubility ionic compounds and bases, they are not going to dissolve nor dissociate in water. So where you're going to find those are going to be in that last row of the solubility table. So you'd find it down here. So the low solubility compounds, they're going to form precipitates. The word precipitate just means that it's a compound that has a low solubility in water. And how we show this is you're just going to write your compound. You are not going to break it apart into its ions, so you're not going to dissociate it because it is insoluble in water. And you just make sure you keep the state as solid. Okay, so calcium sulfate, it's placed in water. If you take a look at calcium sulfate, so finding sulfate here, okay, that's going to be SO4. And if I trace my finger down, okay, most things are soluble with it. However, if I keep on going down, boom, we've got calcium here as one of our exceptions, which is slightly soluble. So we're going to call it insoluble, and that's why they're not dissociating calcium sulfate, and they're leaving the state as solid. Okay, so if you find an ionic compound in the last row, which I've highlighted in blue here, it's going to be insoluble in water. Therefore, you do not break it apart into its ions. So you do not dissociate it. Same with silver iodide. Okay, so let's get rid of this. So iodide, we find that here, okay, most things are soluble, but let's just check our list of exceptions, and we find silver right there. Therefore, we call it insoluble, we keep it together, and we put the state as solid. Okay. So for our examples, we're always going to be referring to the solubility table on page 6 of your Chem 30 data booklet to check the solubility specifically for ionic compounds. Bases do count, or strong bases do count as ionic compounds because it's a metal with hydroxide. So it's a metal with one or more nonmetals, which is the definition of an ionic compound. So refer to page 6, Chem 30 data booklet. Okay, so let's take a look at zinc sulfate. So let's get rid of this. So sulfate is right here. Most things are soluble with it, but let's just check our list of exceptions. So let's go down here and see, do we see zinc here? So I don't see zinc in our list of exceptions, therefore we can call it soluble. So if an ionic compound is soluble in water, that means we can say it dissociates. So zinc sulfate, what I'm going to do before I write the rest of the equation is I'm just going to check what the charge is on zinc. Let's see. So zinc is right here on the periodic table. It's got a charge of 2+. Okay, and for sulfate, let's see. Sulfate has a charge of 2-. So if you wanted to do this here, zinc 2+ and sulfate 2-, which is equal to 0, which means the compound is balanced. So we don't have to do anything to increase the subscripts or write any subscripts in order to balance the compound, because 2 minus 2 is equal to 0. It's already a neutral compound. Okay. All right. So what these examples are trying to get us to do is to write an equation for what happens when we put these substances in water. So I'm going to write water liquid just above the arrow. And because zinc sulfate is soluble in water, we're going to write a dissociation equation. So zinc 2+, and we're writing it as aqueous because ions are always aqueous, plus sulfate 2- aqueous. So super important with ions, always remember to put the charges as well as the states. Oftentimes those get forgotten about. Okay. Next one, we have copper 2 hydroxide. So looking at our solubility table here, let's zoom out. Okay, so hydroxide is here. Copper is not in group 1, nor is it ammonia. So then I'm going to go down and be like, okay, it falls under most. So that means copper, here, let's go back. Copper 2 hydroxide, since we found it in the last row, it is insoluble in water. Okay, so copper, now the Roman numerals, remember, that indicates the charge, not how many atoms of copper that you have. So copper, this is 2+, and then hydroxide, it's OH. Now remember that hydroxide, that has a 1- charge to it. Therefore, we know that 2 minus 1 does not equal 0. So this is when we're going to have to do crisscross applesauce. Okay, so this is when we just pull down the numbers. We don't take the charges, so the plus or the minus, and we put them behind either the element or the polyatomic ion. Now, since hydroxide is a polyatomic ion and there's more than one of them, that's why we're going to write those brackets and then put a 2 after it. Okay, because we want to indicate that we have 2 hydroxides. Without the brackets, this would just have 1 oxygen and 2 hydrogens, which we don't want. We want to say, okay, 2 hydroxides. Okay, so that's going to change the charge to -2 coming from the hydroxide, which means this is balanced, so we're all good on that front now. Okay, so by the way, you can always assume an ionic compound at room temperature when it's not in water is a solid. Okay, and right over top of the arrow, I'm just saying water. And that's to indicate, okay, we're putting copper 2 hydroxide in water. All right, now, since we said that it was insoluble in water, we're not going to do anything. It's going to remain the same. That is not copper sulfate. That is copper 2 hydroxide. So we're not breaking it apart into its ions because it is not soluble in water. Okay. Sodium phosphate, same exact process. Let's get rid of this. So phosphate is going to be here, group 1 ions. Sodium is part of our group 1 ions. So where we can find it is, here's group 1, there is sodium. So sodium, that likes to have a +1 charge. And for phosphate there, we can find it right here. Phosphate likes to have a 3- charge. So obviously we know 1 minus 3, that does not equal 0. So we're going to have to do crisscross applesauce. We are only bringing down the numbers, not the charges, so the plus or the minus. Okay, so if we put 1 here, like since we still have 1 polyatomic ion, the phosphate, we're not going to include brackets. But for the 3, I'm going to place that right behind the sodium, and since sodium is not a polyatomic ion, you do not put brackets there. Okay, so that's going to change this since now we have 3 sodiums, so we have 3 +1s, which if you add all those up, that's going to give you +3. Okay, which 3 minus 3, that's equal to 0, so this is balanced now. Our state is solid. We're throwing it in water. And since we found, going back to our solubility table, so since sodium is a group 1 ion, we do find it in the second row here, so it is very soluble in water. So that means that this is going to dissociate. Okay, now one last thing we got to do before we move on here is notice how there's 3 sodiums going in but only 1 sodium going out. So we do need to balance our dissociation equation by placing a 3 in front of the sodium. So just remember, with balancing equations, you balance equations using the coefficients, so the big numbers in front of whatever chemical substance you're talking about. You do not balance equations with the subscripts. You only balance like the compound with the subscripts. You don't balance the entire equation. So just watch out for that. So 3 sodiums going in, 3 coming out, 1 phosphate going in, 1 coming out. We are good. All right. So essentially what we're talking about here is how do you know like which specific substances are going to be aqueous or soluble in water versus insoluble in water. So we just went over ionic compounds and bases. Now we're going to go over acids or acidic solutions. And then we're going to go over molecular compounds and elements. Okay. So with strong acids, in Chem 20, we have 6 strong acids that we need to be aware of. How do we know which are our strong acids? Well, we are going to go to page 8 of the Chem 30 data booklet, and anything above the gray hydronium line, that is going to be a strong acid. So you don't have to memorize these, you just have to know where to find them in your data booklet. Okay, so our 6 strong acids are perchloric acid, hydroiodic acid, hydrobromic acid, hydrochloric acid, sulfuric acid, and nitric acid. Those are our 6 strong acids. Anything below the gray hydronium line is going to be considered a weak acid. Okay, now I'm saying above and below because when you have your own Chem 30 data booklet, you could turn it to the side to make it so that this is your top of your page. Okay. All right, so the 6 strong acids, they're going to ionize completely to produce hydrogen ions and an anion, so a negative ion. Okay, and how we're going to represent this is we're going to show them as hydrogen ions and the negative ion. Okay, so for hydrochloric acid, that's HCl, what would be present in solution? Since it's a strong acid, it's going to ionize completely. So we're using the word ionize because acids refer to molecular compounds. Okay, and also just while I'm thinking about it, acids are always in an aqueous state unless otherwise stated by the question. Okay, so if you put hydrochloric acid in a beaker, how it would exist is with hydrogen ions as well as chloride ions. So with these beakers here, they're showing you what chemical species are going to be present if you put whatever substance in water here. Okay, with nitric acid, that's another one of our strong acids. You can find it right here. Hydrochloric acid was right here. Okay, and with nitric acids, once again, since it is a strong acid, it's going to ionize completely, and therefore it's going to exist as H+ and nitrate. Okay. So if we were to write the ionization equations for these, what it would look like, so for hydrochloric acid, we would go hydrochloric acid, aqueous, and since it's aqueous, we don't need to write water over top of the arrow. So then we're just going to go H+, aqueous, chloride, aqueous. Okay. So keep in mind, if you're asked what entities are present when a substance is put in water, it's just expecting you to write something like this. You don't have to write the beaker, just what is present. Okay, however, if you're asked for a reaction equation when something's put in water, this is more so what the question's looking for. Okay, Same thing with nitric acid, HNO3, aqueous, because acids are always aqueous. If we were to write the ionization equation, this is what it would look like. Okay, and before we move on, I'm just going to write down what I've been saying here. So acids are always aqueous unless stated otherwise. And you can find the 6 strong acids on page 8 of the Chem 30 data booklet. They're above the gray hydronium line. Okay, so those are our high solubility acids, the strong acids, whereas weak acids, they do not completely ionize in water. They do a little bit, but since they don't completely ionize in water, we show them only as whole molecules in solution. Okay, so remember, your weak acids are going to be anything below this gray hydronium line, and specifically in the acid formula column. Those are all going to be your weak acids, and this table also continues on to page 9, so all of these here are weak acids as well. Okay, so acetic acid, that is a weak acid, and if you threw it in water, we would just keep it all together. We would not ionize it. Okay, so weak acids, even though they ionize a bit, we show them as whole molecules in solution. Sulfurous acid, not to be confused with sulfuric acid, that is another weak acid. So we keep it together when we're representing it as being put in water. Okay. So for some examples here, okay, so we've got hydrogen chloride gas, and we're just being asked, okay, what happens, or write the reaction for what happens when you put it in water. So for this, it's going to be a 2-step process because we want to show that it dissolves. Okay, so step 1 is going to be hydrogen chloride gas, and we're putting it, or we're bubbling it through water is what would happen. And it is going to dissolve in water because it's one of our it's going to become one of our 6 strong acids. Right, so it's aqueous, and since it's one of our 6 strong acids, it's also going to ionize. So we got to represent that. And I don't need to write water over top of the second, this second reaction arrow, because aqueous means water is present, or this substance is dissolved in water, so that's how I know water is present. Okay. Now with liquid hydrogen acetate, so for hydrogen acetate, where we're going to find that is going to be under acetic acid. Okay, so acetate is just referring to the ion that's right here, whereas, so hydrogen acetate just means hydrogen and then acetate ion. Okay, so since they specified that it's liquid, we're going to write this and then just put it in the liquid state. So CH3COOH, liquid. All right, so acids, like I said in the previous page, they're always going to be aqueous unless stated otherwise by the question. This is stated otherwise by the question, but since we know acids are always aqueous, that's how you know it is going to dissolve in water. Okay, so this is just showing that it dissolves in water. But after it's like put in water and dissolved in water, it doesn't do anything other than that. Okay, or we don't show that it breaks apart into its ions because it is a weak acid. How we know it's a weak acid is because you'll find acetate underneath the hydronium line on page 8. Okay, that's how you know. So you could leave it as this, or if you really wanted to be like, yeah, it doesn't ionize, you could write this just as an extra step. But the second equation isn't needed because nothing's changing in there. The next compound or substances that you need to know how it's going to dissolve or not in water are going to be our molecular compounds and our elements. Okay, so for high solubility compounds, okay, these are going to be our molecular compounds that are able to dissolve in water but don't dissociate. And actually, since we're talking about molecular compounds, we should actually change that to ionize. Okay, so our high solubility molecular compounds, what those are going to be our compounds that can do hydrogen bonding as well as sugars. So sugars like glucose, sucrose, fructose, that sort of thing is what you'd be looking for. High solubility elements are going to be our group 17 elements. Okay, so group 17, let's go back to our periodic table. Group 17 is going to be right here. So that's going to be your fluorine, chlorine, bromine, iodine, and astatine. Those are your group 17 elements. So those are very soluble in water. So for example, let's say we had chlorine gas. So chlorine is part of Hofbrinkel, so it's a diatomic element. So let's say we bubbled some chlorine gas through water. How we would represent what's happening to the chlorine gas is because it's a group 17 element, we would say, yeah, it dissolves in water. So it becomes aqueous, however, it's not going to ionize. Okay. So the only molecular compounds that ionize are going to be your strong acids. There's no other molecular compound that ionizes. For our low solubility compounds, those are going to not dissolve in water and don't, it says dissociate, but we should put ionize there. So it's not going to have any hydrogen bonds. Okay, so essentially if it falls outside of group 17, it can't hydrogen bond, which, as a reminder, hydrogen bonding occurs in any molecular compound that has hydrogen directly attached to nitrogen, oxygen, or fluorine. Okay, so if it's not a compound that can hydrogen bond, or if it's not a sugar, it is going to be low solubility. So, for example, we have sucrose. So if it ends in OSE, that's how you know it's a sugar. Maybe we should write that down. Name ends in OSE. Okay. So solid sucrose is placed in water. Since it is a sugar, it does have high solubility, but because it's not an acid, it's not going to ionize. Okay. So how you know if something's an acid or not is it typically either begins with H or it ends in COOH. That's how you know if something's an acid. So maybe let's go up to, our acid section. How to tell if a compound is an acid. Compound will either begin with H, like the chemical formula for the compound, or it will end with COOH. That's how you know if something's an acid or not. All right. Now, if we have wax placed in water, so with wax, that can't do any hydrogen bonding because hydrogen is not directly bonded to either nitrogen, oxygen, or fluorine. It's not a sugar because the name doesn't end in OSE. Therefore, it's just going to clump together and remain solid. Okay, another way that you could know that this doesn't dissolve in water, if you were just given the chemical formula for it, is you could use your trick that you learned from, I believe it was the first unit there. Any carbon-containing compound that has carbon with only one other element, that is going to be nonpolar. Okay, so C25H52, that is nonpolar. Remember how like dissolves like? Well, nonpolar cannot dissolve in polar. Water is polar. Okay, so let's also rate that. That's another way that you can look at molecular compounds and figure out if they dissolve in water. Okay, so one last thing I'm going to add down below here, just because some of this information can get overwhelming. So I've already said this before, the only type of molecular compound that we're going to show that ionizes is going to be strong acids. So how do we tell if something's an acid or not? It's either going to begin with H or end in COOH. And how do we know if it's a strong acid compared to a weak acid? Well, you go to page 8 of your data booklet, and anything above that gray hydronium line, that is going to be a strong acid. All right, moving on to elements. Okay, so elements, they're either atomic or molecular. So atomic meaning like if they're just by themselves and there's only one atom of them, that's what they're saying with atomic. If they're molecular, those are like our diatomic elements or our polyatomic elements. Okay, so diatomic elements, that's Hofbrinkel. Polyatomic elements, that's going to be P4 for phosphorus when it's by itself, not in a compound, S8 for sulfur, and O3 ozone. Okay, so elements, they are never shown as ions. Okay, they may or may not be soluble in water. Just remember that some elements are molecular and some are atomic. Okay, so metallic elements, when you put them in water, they're not going to be able to dissolve in water. Because if you think about taking a chunk of iron and throwing it in water, it obviously doesn't dissolve. So same kind of logic here. That's how you figure it out. Okay, whereas for when it's a gas, such as oxygen gas, those can dissolve. Okay, so let's write out what's happening here as equations. So silver being placed in water, if you were to just state what entities are present, you just write silver solid. Okay, but if you're asked to write the equation, you just write silver solid, okay, gets put in water. It's still going to be silver solid. Okay. And what's happening here is we have oxygen gas being bubbled through water. So it becomes aqueous. Okay, so essentially solid elements, they're not going to dissolve in water. However, if the element is gaseous or liquid, yes, it's going to dissolve in water. So let's write that down. Sure, here. So solid elements don't dissolve in water, but liquid or gas elements can. And we'll just write liquid. Okay, so if you're wondering how do you determine if an element is solid, liquid, or a gas, how you're going to do that is you can go to your periodic table. Okay, and let's see. So it depends on what you're using. For your periodic table, you could either use the Chem 30 data booklet or the Nelson periodic table. They have different ways to show you what's a solid, liquid, or a gas. Okay, but metallic solids, those are all going to be yellow. So most of what's on the left-hand side of the staircase there, those are all solid metals. Whereas anything that is colored in green, that's going to be a non-metallic solid. So that's just to the right of the staircase line, so this bolded line right here. What's going to be a gas is going to be colored blue, and then liquids are going to be like that pink shade. Okay, so the only metal that is going to be a liquid is going to be mercury right here. And for nonmetals, the only liquid at room temperature is going to be bromine. If you wanted to check out the Nelson periodic table, it's got a slightly different system, but it does say what its system is. So solids, the symbol is going to be black. Liquids, the symbol is going to be blue. So for example, let's find bromine. Right, the symbol is blue, indicating that it's a liquid. And then gases are going to have the symbol in red. Okay, so that's how you tell with either periodic table. I would say, just because I recommended the solubility table in the Chem 30 data booklet, maybe stick to using the Chem 30 data booklet periodic table as well, just to kind of keep things consistent there. Also, it's a little bit easier to read because it's in a bigger font than the Nelson periodic table. All right, so some examples here. So ammonia, that's NH3. Okay, that's going to be one of the compounds that you have to memorize what the common name is and what it translates into for the chemical formula. Ammonia is most often a gas. Most of the time, questions will tell you. Okay, this one just happened not to. Ammonia can exist as a liquid, but more often than not, we can assume it's gas. Okay, so ammonia, that is a molecular compound. Because it does not begin with H or C or end in COOH, we know it's not an acid. Okay, so now we're like, okay, it's a molecular compound, it's not an acid. So what that means is it can dissolve in water, but it's not going to ionize. Okay, how I know that it can dissolve in water, so let's write water here. So dissolving in water, it turns into aqueous. How I know that it dissolves in water is two parts. One, I know that ammonia is polar. You can figure this out by drawing out the Vesper structure of ammonia. Two, the second reason why I know that ammonia will dissolve in water is because it can hydrogen bond. So if we're drawing the Vesper structure of ammonia, it's going to look like that. Okay, nitrogen is more electronegative than hydrogen, so if you're drawing dipole arrows, that's what they look like. So the resultant vector, kind of showing what side of the compound that the electrons are kind of leaning towards, shows you that all the electrons within the bonds between nitrogen and all the hydrogens, they're kind of skewed more towards the hydrogen. Okay, so that means that this is polar, because polar compounds, all it means is that the electrons are unequally distributed throughout the compound. That's it. Okay, and we're just saying, okay, they're more skewed towards the nitrogen side of the compound. So let's write out as, okay, how do we know? So NH3 is polar. So that comes back to like dissolves like. And also, ammonia can hydrogen bond. And since water can also hydrogen bond, and like dissolves like, that's why it dissolves in water. Okay, reminder, hydrogen bonding is in molecules or compounds where hydrogen is directly connected to either nitrogen, oxygen, or fluorine. Okay, with chlorine, we did this as an example previously, but this is a group 17 element. Therefore, it is highly soluble in water. Okay, so chlorine, it exists as a gas just at room temperature. How you know it is because if you look at your Chem 30 data booklet, it's colored blue, which is for gases. Okay, so water. And Hofbrinkel, so chlorine is one of our diatomic elements. And how we remember our diatomic elements is the memory device, mnemonic device, Hofbrinkel. So, how do we know? Group 17 elements are very soluble. Okay, and then with wax, that is a nonpolar substance. How we know it's nonpolar is because it's carbon with only one other element. If it was carbon with 2 or more other elements, then it'd be polar. Okay, for the purposes of Chem 20, that's how we're figuring it out, or that's our shortcut we're taking. So because it's insoluble in water, we keep it together and we put it as a solid. Okay? But remember, for any molecular compounds that are not a strong acid, we do not ionize them. So we do not break them apart into their ions unless it's a strong acid. Okay? Any other molecular compound, you keep it together. So how do we know? Wax is nonpolar. And like only dissolves like. Okay. So this table below, it starts getting into acids and bases as well as neutral substance. It is a practice question, but I do find it helpful just to go over it with students. Okay, so I'll fill out this table with you guys just to kind of start getting you introduced to the concepts, or more introduced, I guess, to the concepts of acids and bases and their empirical as well as their Arrhenius theoretical definitions. So empirical definitions, that's just like, okay, what can we see that they do, essentially? Or what can you detect with your 5 senses that acids, bases, neutral substances can do? But with this one, it's more so what we see. So Arrhenius theoretical, you're not going to be able to see this, okay? But it's just kind of theoretically what's happening. Theory, can't see. Okay, so for acids, we can test them with something called litmus paper. Now, litmus paper is essentially a piece of paper that's either going to turn red or blue depending on the type of substance that you put it in. So for acids, the litmus paper turns red. So you can kind of remember it like red acid. So if you slightly incorrectly pronounce acid wrong, it sort of rhymes. Okay, not perfect, but whatever. Okay, now Arrhenius's theoretical definition. Arrhenius is a scientist that studied acids and bases to come up with a definition for them. Okay, now for Arrhenius, he said that acids, they ionize in water to produce hydrogen and whatever anion. That's a negative ion. So ionize in water to produce H plus ion and an anion. I can't say a specific anion because it just depends on what the hydrogen's paired with. With bases, they're going to turn litmus paper blue. So you can remember this as B for blue for base. And Arrhenius defined bases as substances that dissociate to produce hydroxide ions and some sort of cation. Okay, so I'm using the word dissociate specifically because bases, most bases that we're going to talk about in chemistry 20 are ionic compounds. However, not every single base is an ionic compound. So dissociate to produce hydroxide ion and a cation. So a reminder, cation is just a positive ion. Alright, now neutral substances. These are neither acids nor bases. So when you put litmus paper in a neutral substance, it's going to stay the same color. And Arrhenius's theoretical definition with neutral substances is if it's a neutral ionic substance that is soluble, it's going to dissociate. And if it's a neutral molecular compound, which is not an acid, it is not going to ionize. So when I say ionic compound here, because we're talking about neutral substances, it's an ionic compound that is not a base, because some bases are ionic. They also have to be soluble. It's going to dissociate. And then for neutral molecular compounds, which are not acids, does not ionize. So a reminder, dissociate is specifically for ionic compounds that are soluble in water. Ionization is for molecular compounds that can break apart into their ions, which are going to be your strong acids.